So finally moving on to the very last question now for this AS Core Pure paper, we've got to question 10, which is quite a long question, and it's dealing with matrices. So again, this is a very context heavy question. So it's looking at the population of chimpanzees in a particular country, which consists of juveniles and adults. So we're given this model here for a population, and the very first part just asks us to interpret the meaning of the constant A in the context of the model. So it's important to know what's going on. So my Jn plus 1 gives me my next population figure for the juveniles, and my An plus 1 gives me the next population figure for the adults. So this A here, so let me just get my pen. So what I'm going to do is I'm going to write down the sides for this question because it is quite like long. Obviously I haven't got much room here down at the bottom. I'm just going to write down the sides. So I'll do it in yellow. So part A. So what does this constant A mean in the context? Well, this A just represents the proportion. It represents the proportion of juvenile chimps. Proportion. So the proportion of juvenile chimps that survive and remain juvenile chimps. So quite a long opener, and remain juvenile chimps. Okay, so that's part A. So for part A represents the proportion of juvenile chimps that survive and remain juvenile chimps. Okay, so there's one marker there. Part B, so we're given a bit more information. We're told at the start of the study the total number of chimpanzees in the country was estimated to be 64,000, and then according to the model, after 1 year the number of juvenile chimps is 15,360 and the number of adult chimpanzees is 43,008. So we have to find, in terms of the inverse of this 2x2 matrix here. So to find the inverse of a 2x2 matrix, the first thing we should do really is just work out the determinant. So if we work out the determinant for this matrix, determinant, well, the determinant, remember, is this element here, so A times 0.82, so that's 0.82A, and then we minus 0.08 times 0.15, and if you do that on your calculator you'll get minus 0.012. Okay, so that's the determinant. So now, to work out the inverse, we do 1 over the determinant, so 1 over the determinant, let's call it det, and then we times this by the inverse matrix, or the matrix that we have to just do a little bit of work to. So the A and the 0.82, they change positions, so this is going to be 0.82 and that will be A there, and then my 0.15 and my 0.08, they become negatives, or if they were negatives they become positive, so think of them as the conjugates. So that would be minus 0.15, and then this one here will be minus 0.08. Okay, but we know the determinant. The determinant here is 0.82a minus 0.012. So if we plug that in now, I'm going to get 1 over 0.82a minus 0.012. Okay, and there we have it. If we just multiply this again by the matrix, 0.82 minus 0.15 minus 0.08, and then finally A. And that's it. So that is the inverse here of this matrix. So that's B part 1. B part 2, hence or otherwise find the value of A. So find the value of A. So it's a hence or otherwise question. So what that suggests is that this part of the question here, the previous part, will be helpful for solving this. Well, we're going to use this information that they give us now. So using the inverse now, what we can do is use the inverse. So if I write down the inverse, so A 0.15, 0.82, so the inverse here of this matrix, and I times it by these population figures that they give us, so 15,360 and 43,008, we can work out a value for A, right? So multiply that through by 15,360 and then 43,008, we can work out a value for A. Now it's worth noting this part now will become quite tricky. There's a bit of manipulation that you've got to be careful with. So we know this now. This is what we just previously worked out, and this is why it's a hence or otherwise question. So if I write this out in full, this is going to be 1 over 0.82a minus 0.012. And then it's this matrix here, so 0.82 minus 0.08 minus 0.15 A, and then we times it by this. Okay, so I should just have enough room. And 43,008. Okay, and if I close that. So what I'm going to do now is just multiply across here, and we'll keep this 1 over just on the outside for now. So I've already done the calculations ahead of time, but what this will be is I'll write them down anyway, just so it makes it clear. So I'm just going to do this symbol here just to represent this again, just so I've got more room. In the brackets now, so it's going to be 0.82 times this, and then minus 0.15 times this. So 0.82 times 15,360 minus 0.15 times 43,008. Okay, and then again, let's work out the bottom element of this matrix. Minus 0.08 times this, and then A times this. $15,360 again. And then plus 43,008 lots of A. Now we know this here now, this is the total population. And we've been told that the total number of chimpanzees was 64,000. So 1 over 0.82a minus 0.012 times this should be equal to 64,000. So if I just simplify this and then write my 1 over again, so what this is equal to is 1 over 0.82a minus 0.012 times, so 6,144, and then minus, in fact I'll do the positive first, so 43,008 A minus 1,228.8. This is equal to 64,000, okay? So this is equal to 64,000, because that's the total population, right? So, but we just said that these two added together, again, is the total population. So, because obviously the juveniles and the adults must be added together to give the total number of chimpanzees. So, we can rewrite this again as 1 over. So this is going to get quite tedious. It is quite a long question. 82a minus 0.012. Adding these together now, what I'm going to get is 4,915.2 plus 43,008A. This is equal to 64,000. So now this just has to be solved. So what I can do is I can times both sides by 0.82a minus 0.012. So what I'm going to do is I'm just going to clear everything here and then start multiplying through. So multiplying through, well, the left hand side would just cancel. I'd get 4,915.2 plus 43,008A. This will be equal now to the right hand side times by that bracket. So I'm probably just going to run out of room again. This is quite a long question. So it's going to be 64,000. If I just do it in black, just so you can see on the white part here. So it's going to be 64,000 times 0.82a minus 0.012. Okay, so I've got to do 64,000 and then expand this bracket here. So I'll just move this across a bit more. Hopefully I'll have enough room. So this side here will remain the same, 4,915.2. So just rewriting that side again. This side now, if you expand this through, what you'll get is 52,488. And you'll also get minus 768. Okay. Now we've just got to solve this equation in terms of A. So really easy. So solving this now, I'm going to get 9,472 A is equal to 5,683, sorry, 0.2, and then therefore A must be equal to 5,683.2 divided by 9,472, giving us 0.6. Okay. So there's our value for A. Okay, so we've still got quite a bit of this question to go yet. We now have to calculate the change in the model of in the number of juvenile chimpanzees in the first year of the study using this model. So this is B part 3. Well, in our model for the juveniles, we had 1 over the determinant times 6,144, so that was the juveniles, and then the adults was the 43,008 A minus 1,228.8. Okay, so my juveniles is this number here. This is the key number. So I'm going to do 6,144 divided by the determinant. So I'm doing 1 over the determinant times this, or basically this number divided by the determinant. And what this will give me is this will give me the previous number. And then using that number, we can just work out the change in the number of juvenile chimps. So this will be 0.82. So it was 0.82A, so that's 0.6 for A, because that's what we worked out here, minus 0.012. Okay, put this on your calculator. What you'll get is 6,144 divided by 0.48. And if you put that in on your calculator, what you get is 12,800. So there were 12,800 chimps. So we started with 12,800. The next year there was 15,360. So how do we work out the increase? Oh, we're just going to subtract them, right? Nice and easy. Do this on your calculator, and what you'll get is 2,560 chimps. So that's the increase. So that's my increase. Okay. Part C asks us to comment on the short-term suitability of this model. Well, it does say that the number of juvenile chimpanzees is known to be in decline in this country, but our model has just shown an increase to 2,560. So what we can say is that the model is not suitable as the model has an increase. Okay, so that's part C. So it's just a brief 1 mark comment, and because ours is increasing, whereas they're known to be decreasing, they're in decline, then we can say it's not suitable for the short term. Okay, so if we just clear that, and then finally for part D, 2 marks, we're asked to refine the matrix system for the model to reflect this information. And what we're told is that the study of the population revealed that adult chimpanzees stopped reproducing at the age of 40 years. So if they stopped reproducing it after 40, what we could do is introduce a new, we almost call it a variable, right? So what we had was we had juveniles, we had adults. I'm going to introduce a third one now. So if we call them, say, elderly or mature, we'll call them mature. So okay, so mature chimps. Okay. So if we call this M, N, and what we're going to do now is represent this as a 3 by 3 matrix here. So it's not 2 by 2 now, it's going to be 3 by 3. And it won't be jn plus 1 and an plus 1, it'll be jn plus 1, an plus 1, and mn plus 1, okay? And where it's jn and an, we've got an mn here. So we can represent this now. So if I do it down here, so I've got extra room. So it'll be j, n plus 1, a, n plus 1, and then m, n plus 1. This is equal to a 3x3 matrix now. So this 3x3 matrix, for the values, you can put pretty much anything in because you're just representing what this system could be, this model, right? But there's a few zeros that need to go in. And you need to think about what you're multiplying it by. So it's going to multiply similar to how it did here. So it'll be jn, an, and mn. Now, the key thing to think about is obviously the fact that a juvenile chimp can't go from juvenile to mature. It clearly can't skip that middle life stage. And similarly, a mature chimp can't regress to a juvenile chimp. So we're going to need some zeros in so that once we perform the multiplication, those two ideas aren't possible, okay? So if I say that's A, that's B, if I put a 0 in here now, what that'll happen is when I multiply this row with this column, I'd get an A lot of jn, a B lot of an, and 0 lots of mn. So what we're saying is that the juveniles cannot just go, they can't go from juvenile to a mature. So that's good. Doing the same here now, we'll get a C, we'll get a D, and we'll get a 0. And same again here now, we can't go from mature to juvenile, so that has to be a 0 as well. And then this can just be E and F. So my A, B, C, D, E, and F, they're just representing a value. That's not important, but the idea that these zeros here and here and here are important. It's illustrating the fact that a juvenile chimp can't become a mature and vice versa. A mature chimp can't become a juvenile chimp. But there we have it. So that's question 10 fully complete, and that finishes the core pure paper. If you're new around here, guys, be sure to subscribe. I'm going through all the 2019 further maths papers.